Honors Physics. Today we're going to do some electric field problems. So there's two basic types of electric field problems. One where a particle is experiencing a field and one where it's causing a field. We're going to do both. Okay, so let's start with the one that is experiencing the field. So here's the problem that I have. A helium nucleus moves through a field of positive 45 newtons per coulomb. Now, what does that mean? That means that any particle moving through that field will experience a force of 45 newtons for every 1 coulomb of charge. What is the acceleration of the nucleus, and what is its speed after 10 seconds if it started from rest? Okay, so we have two formulas for the electric field. We have E equals F over Q. That is the formula for a particle that is experiencing the field. I'll tell you how to remember the other one when we get to the other one. Okay? So this is the particle, the helium nucleus. A helium nucleus, you remember from chemistry, is 2 protons and 2 neutrons. Now you remember the neutrons don't have a charge, so the charge is coming just from the protons. So we want what the acceleration is going to be. In order to get the acceleration, we need to know the force. So I'm going to solve for F in this equation. F equals E times Q. So what's E? E is given 45. Newtons per coulomb. And my charge is my 2 protons. Now on your formula sheet that I gave you, we saw what the charge of a proton was. It was positive 1.6 times 10 to the negative 19th. We have 2 of them. So that's 2 times 1.6 to the negative 19th, which will give us 3.2. So now all I have to do is hit this into my calculator, which I happen to have on me. So 45 times 3.2 to the negative 19th, and that gives me 1.44 times 10 to the negative 17th newtons. Not a very big force, but we don't have a very big charge. Now, I want to know what is my acceleration going to be. To get the acceleration, I'm going to use our old formula, F equals ma. So A is going to be the force divided by the mass. So 1.44 times 10 to the negative 17th divided by the mass. Now the mass of my helium nucleus comes from both my protons and my neutrons. If you again look at the formula sheet I sent you, you'll see that protons and neutrons have the same mass. So I've got 2 protons and 2 neutrons, so I'm going to multiply that by 4. So 4 times 1.67 times 10 to the negative 27th kilograms. Where am I getting that number from again? That's the mass of a proton, which is the same as the mass of a neutron. 2 protons, 2 neutrons, that's where my 4 comes from. So my force divided by 4 times 1.67 to the negative 27th That gives me an acceleration of 2.16 times 10, 3, 6, to the 9th meters per second squared. Okay? Oh, I meant this to be 0.1 seconds. Okay? So that's my answer for part A. Part B. I want to know what is my speed going to be, 10 seconds, 0.1 seconds, excuse me, if it started at rest. So for this, I'm just going to use one of my old kinematics equations. VF equals VO plus AT. It's starting from rest. So my acceleration, 2.16 times 10 to the 9th meters per second squared, times 0.1 seconds. That's going to give me 2.16 times 10 to the 8th meters per second. Now, there's one more thing to talk about with this problem. Because this nucleus is positive and this field is positive, what's going to happen is my particle, say here's my field, my particle is going to move in the opposite direction of the field. Okay? If my particle was negative, it would move toward the field. Opposites attract. Okay, so now let's get to our second problem. Second problem is a little bit shorter. It says a negative 3.2 times 10 to the negative 18th Coulomb particle produces a field. What is the field strength 20 centimeters away? So this particle is causing the field. Since it is causing the field, what I'm going to use is my other electric field equation. E equals KQ over R squared. How do I remember that this is for particles that cause field? It's got a K. K, I know cause begins with C, but it sounds the same. So that's how you can remember causes, experiences. Okay? So all I have to now do is just plug in K, 8.99 times 10 to the 9th, our Coulomb's constant, times negative 3.2 to the negative 18th, all over 0.2 meters squared. I hit that into my calculator. And I get a field of negative 7.19 times 10 to the negative 7th newtons per coulomb. Okay, now this is a negative electric field. One of the other things that I'm going to ask you to do in the problem sheet that I sent is I'm going to ask you to diagram electric fields. So let's diagram this field. So there is my charge. It's a negative charge. Therefore, my field lines are going to enter my charge. If it were positive, my arrows would go in the other direction. Now, the other thing about field lines is the greater this value, the more field lines you have. So I have a relatively low electric field, so I'm only drawing a few field lines. Now, what if there was another charge somewhere nearby? Let's make a positive charge here. What we would see is the field lines would leave my positive and enter my negative. And another thing about them is they're three-dimensional, so there's actually one coming out and going back in, and one that goes in and comes back out. Okay? All right, so that is our field line problems. If you have any questions, send me an email, send me something on Remind. Okay? Your quiz will be Wednesday. Goodbye, Honors Physics.